Welcome everyone. Today I'll walk through 5 signals from the forthcoming 2026 Siemens EDA and Wilson Reach Group Functional Verification Study. The central question is whether First Silicon success has entered a new operating state. This is not just a discussion about one metric declining. The larger question is whether the nature of verification risk is changing as silicon systems become more processor-rich, software-driven, workload-dependent, and shaped by safety, security, power, and recovery behavior. Let's start with answering the question, why this study feels different. For most of the past 20 years, the verification story was difficult but familiar. Designs became larger and more complex, but verification teams also became more disciplined. Methodologies improved, planning improved, coverage, assertions, formal UVM, and emulation became more widely adopted. The industry was not eliminating respins, but it appeared to be absorbing complexity well enough to keep First Silicon success in a relatively stable range. That is why this study feels different. The latest results suggest that the familiar pattern may no longer hold. Verification risk is increasingly shaped by system-level hardware plus software interactions, not just by more RTL complexity. So this brings us to the first signal. This is the headline signal. For many years, reported First Silicon success hovered around 30%. Recent studies show a sharp decline, 24% in 2022, 14% in 2024, and 5% in the forthcoming 2026 study. The exact percentage should be interpreted carefully. This is survey-based evidence, not a project-by-project census. But the directional pattern is hard to ignore. The key question is not simply, why did one number move? The deeper question is whether the industry is still facing a larger version of the same verification problem, or whether the risk profile itself has changed. The 5% number is striking, and it will naturally get attention. But stopping there would miss the bigger story. The study is most useful when the results are read as a pattern. First Silicon success declines, accelerator class participation rises, embedded processors become nearly universal in the reported population, the verification ecosystem broadens, and firmware, safety, and security become more visible respin contributors. A single data point starts the conversation. Multiple related signals make the case that verification risk may be changing in nature. One obvious explanation is that the survey includes more CPU/GPU/AI accelerator class projects, which we have labeled as Signal 2. Participation in those projects rose sharply, reaching 61% in the 2026 study. That matters because accelerator class projects concentrate many difficult system behaviors: software enablement, workload dependence, memory complexity, power and thermal management, safety, security, and bring-up. But the subgroup data complicates the simple explanation. Reported First Silicon success is similarly low for CPU/GPU/AI and non-CPU/GPU/AI responses, 5.3% versus 4.1%. That difference should not be treated as statistically meaningful. So accelerator class projects are not the sole explanation. They may be the leading edge of a broader shift. More designs are beginning to behave like software-driven silicon systems. Signal 3 shows a striking result related to embedded processor core content. In 2022, 26% of respondents reported designs with no embedded processor. In 2026, that number dropped to 3%. Put differently, 97% reported one or more embedded processors. We should be careful here. The study does not identify the type, scale, or role of each processor. Some may be large application class cores. Others may be small controllers, service processors, DSPs, safety islands, boot controllers, or firmware engines. But even a modest embedded processor can change verification if it participates in boot, configuration, power management, error handling, safety, security, or recovery. The design is no longer simply stimulated from the outside. It can boot, configure itself, run firmware, change modes, and interact with workloads. That brings software-controlled behavior into the verification problem. Signal 4 observes the verification ecosystem broadening. System Verilog remains foundational. That point is important. This is not a replacement story, but the reported verification ecosystem is broadening. System C, C/C++, Python, and PSS are all more visible. That reflects more activity above and around the RTL test bench. Modeling, emulation, prototyping, workload execution, firmware-driven validation, portable stimulus, automation, and system-level debug. The safest interpretation is that System Verilog remains central for block and subsystem-level RTL verification, while more full system confidence work is happening in a broader ecosystem. The story is expansion, not replacement. For Signal 5, the 2026 study also shows firmware, safety, and security-related issues becoming more visible contributors to ASIC respins. Firmware rises from 12% to 35%, safety from 6% to 31%, and security from 8% to 22%. These are not mutually exclusive root cause categories. A firmware-related respin does not necessarily mean the firmware team wrote bad code. It may mean firmware exposed a hardware/software contract gap. The same is true for safety and security. These issues often cut across diagnostics, recovery, operating modes, software control, access policy, and fault response. These are not simply bug categories. They are symptoms of convergence. Another interpretation is that the population of companies building silicon is changing. More system companies, hyperscalers, AI infrastructure companies, automotive companies, and software-driven organizations are building custom silicon. Many are highly sophisticated. They understand workloads, software, AI, systems, and application requirements deeply. But system sophistication is not the same as semiconductor verification maturity. Verification maturity is built through planning, measuring, debugging, closing risk, and learning where interactions usually hide. If the population of silicon projects expands faster than verification maturity spreads, aggregate outcomes can decline even while the most mature verification teams continue to improve. For years, functional verification has often been framed around closure. Coverage closure, regression closure, assertion closure, formal closure, block closure, and subsystem closure. All of that remains necessary. But the 2026 signals suggest that closure alone may no longer be the complete measure of pre-silicon confidence. The challenge is connecting evidence across abstraction levels. RTL verification, firmware execution, workload behavior, safety and security analysis, power and recovery behavior, and post-silicon feedback. The goal is not just to prove pieces of the design. The goal is to build confidence that the integrated hardware/software system will behave correctly under real operating conditions. The practical implication is that teams need to explore three classes of behavior earlier. First, software-driven behavior. Boot, configuration, firmware execution, software visible control, workloads, status reporting, and error handling. Second, operational behavior. Power states, reset, recovery, memory pressure, thermal conditions, performance modes, and realistic operating sequences. Third, assurance behavior. Safety mechanisms, security policies, diagnostics, fault handling, access control, and recovery from abnormal conditions. The challenge is not simply running more tests. It is exposing the interactions that appear when software-driven, operational, and assurance behavior meet. The verification target has changed. The question is no longer only whether the design was verified. It is whether the software-driven silicon system was understood before silicon became the first place where all of its interactions were visible. That is the strategic shift behind these 5 signals. 5 signals. One larger question. Are we entering a new verification regime? One final thought. The study also measures adoption of AI-enabled EDA solutions. I have not included that data in these 5 signals because it addresses a different question. The 5 signals describe how the verification problem is changing. AI-enabled design and verification solutions will be an important part of how the industry responds. That deserves a separate discussion. Explore these trends in greater depth in the full white paper, 5 Signals from the 2026 Functional Verification Study. It includes the survey interpretation, subgroup comparisons, definition-sensitive results, and a detailed discussion of what the data can and cannot prove. The white paper is available through Siemens.com and verificationacademy.com.